Greetings everyone, here is the example number 9 from section 4.6. It's from the list of examples that I gave you in our notes. This is one of the ones that we never got to in class, so well, here it is. Just so you can see it, it says you're standing at the edge of a slow-moving river, which is 1 mile wide, and wish to return to your campground on the opposite side of the river. You can swim at 2 miles per hour and walk at 3 miles per hour. You must first swim across the river to any point on the opposite bank. From there, walk to the campground, which is 1 mile from the point directly across the river from where you start your swim. What route will take the least amount of time? So I started to sketch it over here. So you're standing on one side of the river. The river is 1 mile wide, and then you have the campground here, which is down, or at least one mile from where you were directly across. So if you go directly across the river this way and then down this way, this is going to be 1 mile right here. So one possible way that you could get from where you are to the campground would be to swim directly across and then to walk down to the campsite. Another possibility would be to go ahead and swim directly across to the campsite at the diagonal here. And then of course you could swim at any point in between, to any point along the river, rather along the opposite bank in between, and then once you swim to that point, walk the rest of the way. So you have an all swim, you have a swim straight across and then do the most walking that's there, or you have, some little bit, in between swim and then a partial walk. And these different possibilities are how things work. Now, what's helping you out or working for or against you is the fact that you are that you can walk faster than you could swim. So you might think, well, I want to walk as much as possible. So maybe you do swim straight across and walk down because you'll spend the most time or do the most distance walking. But the difference isn't that much. So you think, well, maybe if I minimize the distance, just go from point A to point B directly by swimming the whole thing, maybe that's the fastest route, because there isn't a great difference. 2 miles per hour to 3 miles per hour isn't that big necessarily. So that's a possibility, or some point in between. We're going to let the mathematics kind of dictate how we come up with our answer here. So here's our campground, our fire, and we got to figure out how to do this. So let's suppose for a moment that we are going to swim across to some point that's not directly across, and the distance is going to be x. And so this distance here is going to be x. So I'm going to swim to some point on the opposite riverbank that's x units down from being directly across. Now x could be 0, that would mean I swim directly across, or x could be 1, which means I would swim directly to the campsite, but that's the possibilities there. Well, if that's x, what's left over for this little segment down over here? This is going to be 1 minus x, because the whole distance was 1. And so whatever was left from the 1 mile, that after we take away x, that's what's down to that portion over there. All right, so let's figure some things out here. Since we're trying to minimize the time that we have here, we have to remember something from our pre-cal days, and not necessarily the pre-cal class, but just before calculus. And there was an equation that I like to have students remember as DIRT, and that is distance equals rate times time. And the acronym DIRT kind of helps out with that a little bit. And with this, we can sit here and figure out the time, and we can say time is the distance divided by the rate. And so in order to figure out the total time it's going to take for us to get from where we're starting to the campground, we're going to need the distance that we're traveling for each different swim or walk, and then we know the rate at which we're swimming or walking, and we'll be able to calculate the time for each different piece, each leg of our trip, if you will, and then we'll be able to total those together, and that will give us the total time necessary to do this. So, well, what's going on here? Well, we're going to swim across the orange dotted line that we have there, and so I got to figure out the distance for that orange dotted line, because that's my numerator that I have in my fraction over here to figure out the time. And so to figure out that distance, hopefully you recognize that we have a right triangle here, and so we'll use the Pythagorean theorem. Let's call this distance d, right over here. And, I'm going to get rid of some of this river so that I have some more writing space on the same screen. And so from the Pythagorean theorem, we're going to get d squared is equal to x squared plus 1 squared, but 1 squared is just 1, so we get this. And so d, which is the distance that is going to be swam, is just going to be the square root of the quantity x squared plus 1, like this. So if we swim along that route, we're going to use this distance, root of this x squared plus 1, and remember we said that we're going to swim at 2 miles per hour, so the time it's going to take for us to do this swim is going to be this distance divided by 2. All right, we'll write that down in just a moment when I create some more space. I want to talk about the other distance. Now, if I go ahead and swim the distance that we just talked about, how far would we have to walk? We're going to have to walk from this point down to over here, which we've already called this 1 minus x piece right here. And so the distance we're going to have to walk, I guess I should label this here, might be helpful. This is the swim. The walk distance here that we're going to have to do is going to be 1 minus x. And then again, we said that in the problem we're going to walk at 3 miles per hour, so we'll take that distance and divide it by 3 to get our time it's going to take to do that portion of the trip or to walk that far. So let's move down over here. So the total time, which I'm going to call capital T, is going to be this square root of x squared plus 1, that quantity, divided by 2, distance divided by rate here. And this only works because these rates are constant. If these rates weren't constant, we'd have to use some more calculus tools and with which to work this out. But we're not quite there yet with what we've studied to do everything with that we would like. So luckily this is still a pre-cal level question for that. And then plus 1 minus x divided by 3, that's the time, or rather, the distance we're going to walk divided by the rate at which we're going to walk, which will give us the ratio of the time as the time with which we're going to walk. This is what we're going to minimize. The next thing we want to do is figure out the domain of t. We want to figure out all possible values of x that we can place in here. Let's go back up and look at the picture really quickly. And we've actually already talked about this, but just to remind ourselves, we could swim straight across and then walk the full mile. And so if we did that route, then x would in fact be 0 because we're swimming directly across. So 0 is a possibility for x. And so I'll use a bracket here, square bracket 0. And we also said, if we go back to the picture, that we can swim directly to the campsite, which means that x would be 1 in that case. And so we wouldn't be walking anything. And this would be inclusive like this. Now, theoretically, it is possible for x to be something other than the numbers that we talked about. I think with some simple reason, we could understand that it would be possible for us to swim in this direction and then walk more than a mile if we wanted to. But I think we'd also realize that that's not going to minimize our chances of getting there on time. And then similarly, if I was to swim beyond the campsite over here and then walk back up, that doesn't make sense as a possibility for minimizing the time. It makes sense as something that could be done, but is it going to minimize the time with which we're going to get there? No. And so we're going to leave those possibilities out and just say our domain is the closed interval from 0 to 1. And so now, if this is our domain and it's closed interval, we have a continuous function on a closed interval, we have to have a max, we have to have a min. We're going to try to minimize this. And so what we need to do is we need to find the critical numbers for t, which means we need to take the derivative and find out where the derivative is, 0 or undefined. Take those critical numbers and these two endpoints, 0 and 1, plug them into t, and then figure out which one is the smallest. That'll be our minimum there. The minimum amount of time that it's going to take to do this. And then we'll just have to describe the route. All right, so let's go ahead and work on t prime. And so t prime, we're going to not use the quotient rule. I mean, it is possible, but I would not suggest it or advocate for it. In fact, let me get rid of the prime. Let's just call this t for a moment and do a little rewrite here. Think of this as 1/2 x, the quantity here, x squared plus 1, to the 1/2, and then think of this as 1/3 times the quantity 1 minus x. We've talked about this before, but some of you still want to go ahead and do the quotient rule in problems like this, and it's not wrong, it's just I think you're more likely to make mistakes if you use the quotient rule at this step. So my suggestion would be to think of this as a constant multiple rule instead of a quotient rule. And so now if I take the derivative, I'm going to end up with 1/4, this x squared plus 1, to the negative 1/2. That's the derivative of the outer function with the constant multiple rule, times the derivative of the inner function, which is going to be 2x. And then over here, we're going to have 1/3, and then, well, the derivative of 1/3 times the derivative of what's in the parentheses. The derivative of what's in the parentheses is just -1, so it's just negative 1/3, or 1/3 times -1 for this. And let's do a little bit of algebra here to rewrite this. With the 4 and the 2, we're going to cancel here. That's going to leave a 1 over here and a 2 over here. We're going to bring this negative exponent down to the denominator, as we've said many times. And so we get this expression here. The x is still left in the numerator. That was over with the 2x. And then the 2 from the 4 is still left in the denominator as well. And then we have minus 1/3. And let's do a little bit more algebra here. Typically we form one fraction, set the denominator equal to 0, set the numerator equal to 0, so I'm going to stick with that mode. It's not the only solution method that we could use, but that's what I'm going to advocate here before we actually look for the critical numbers. And so the new denominator is going to be 6 times the square root of the quantity x squared plus 1, because I need a factor of 2 and a factor of 3 and a factor of that square root expression. The first factor here is missing the factor of 3, so first expression is missing a factor of 3, so we'll multiply this. And then this one is missing the 2 root, the quantity x squared plus 1. Now, t prime is never undefined. Whoa, that was a sloppy looking never. Never undefined, because what we're dealing with here is x squared, which is always going to be non-negative, could be 0, but when we add 1, that's always going to be positive, and so we don't have any division by 0 because of that, because this is always positive, and the root of a positive is still positive, and so our denominator is never going to be 0, so we don't have to worry about any places where the derivative is going to be undefined. Now t prime is going to be equal to 0 when this numerator, 3x minus 2 root the quantity x squared plus 1 is equal to 0. And I'm going to have to start a new screen for this. And what I'm going to do is I'm going to bring this term over to this side over here and then square both sides. So I got 3x is equal to 2 root the quantity x squared plus 1. Let me double check that. Yeah. Okay, so we got 9x squared over here is equal to 4 times x squared plus 1, or 9x squared is equal to 4x squared plus 4. A little bit further here, 5x squared is equal to 4, and so x squared is equal to 4/5. I'm 13.5 minutes in. I'm trying to speed this up a little bit. So x is equal to plus or minus 2 over the square root of 5. Of course, we're only looking between 0 and 1, and I'm just pausing for a moment to think about my numbers. The square root of 5 is bigger than the square root of 4, so this quantity of 2 over root 5 will be less than 1, so that is in the interval here. And so what we need to test is t of 0, t of 2 over the square root of 5, and then t of 1, and figure out which one gives us the least amount of time. I'm going to let you guys finish that part up because we're almost 15 minutes in, but you can handle the rest. Go plug that back into t, not t prime. Remember, we're testing the outputs on the closed interval from the endpoints and from the critical numbers to see which one is, in this case, just the smallest. We don't need the max because it wasn't asked for in the problem. We are trying to minimize the time. All right. I hope that was helpful. Go study.